In this video, we will examine the fish recognition and object classification as well as fish tracking functions supported by the system developed in the context of the smartFish project. The basic operations supported in this project include fish detection, recording of fish trajectories, and extraction of individual fish images that are going to be used for morphological feature extraction using shape alignment like fish length and weight. The distance of the fish from the camera is also estimated from stereoscopic vision. Fish tracking can reveal aspects of its behavior and mood. More details are presented here. Image acquisition is performed from a pair of cameras. From the input video frames, fish are detected and image patches with single fish are extracted. These patches can be used to measure morphological features with hardware accelerated shape alignment on the FPGA platform. Before sending these patches to the FPGA, the orientation and the distance of the fish are estimated. The distance is used to measure absolute fish dimensions. At the other path, the motion of the fish is recorded in order to interpret the motions of the fish as its behavior. Here we see the original input video frame at the top and the present and the processed image at the bottom where individual fish patches are extracted. The orientation of the fish is performed using a method developed in the context of this project, and it is based on two angle detection at the head and the caudal fin of the fish. The orientation is the angle between the fish axis and the horizontal axis. The orientation is used by the FPGA platform to select the shape alignment model that matches the specific orientation. Here is a more detailed fish tracking image that can be used to draw conclusions about whether the fish is hungry, stressed, etc. The monitored aspects include the trajectory, the speed, and the acceleration of the fish. Here, more details about fish tracking in 3 dimensions is given, while the z-axis is actually the distance from the camera of the fish and is measured with 1 cm maximum error. Now we will see how we can train different models for fish recognition and tracking. At this point, we see 4 different input videos that were used for training our initial model. They are characterized by different lighting conditions, different backgrounds, and fish population. For example, bottom left and top right are open sea, while up left and bottom right are from the aquarium of the University of Patras setup. The slow motion showed that the procedure was slow. In the second model, we trained with lower recognition confidence threshold. More fish are recognized, but there are also some false detections like at the bottom left and top right videos. However, this worked well for our test environment, as can be seen at the top left and bottom right videos. Next, we see how fish are tracked. The track of each fish is denoted by a line showing the position the same fish has detected. Fish are discriminated by their unique identity. At the top of each bounding box, this identity is presented along with the measured distance from the camera. And now we see a focus in a sub-region where the video frame from a video frame in order to avoid, for example, regions where the fish are confused with their background. Next, we zoom on monitoring the fish tracking of a smaller number of fish in order to see the details of how the distance estimation changes along with the two-dimensional position of each fish. And here we see how we see a focused region with different identities are assigned to fish exiting the focus area while others entering this region. Finally, we see how the fish tracking recorded information is used to represent all the details of the fish motion, including the exact position of the fish in 3 dimensions, the timestamp the fish visited each position, and the estimated speed and acceleration at each point. Thank you for your attention.